in terms of administrative remarks, I don't have anything except for exercise 3 is out, and it's due after the break. Next week is the break. We don't have class at all. Anything I'm forgetting or any comments? Okay. So, yeah?
Has the date of the final exam been set?
I think it's May 8th. Is that correct?
Should be May 8th. We're still waiting for a room confirmation. We will let you know.
Okay. Yeah. Any other questions? All right. So today's topic is boosting. I'm very excited about this topic because it is algorithmic. It's a statistical learning theory, which I talked about on last week, on Thursday, and I kind of derided for being not algorithmic or saying that everything is learnable and in a very broad sense. And what kind of algorithm did we have? The only algorithm that we discussed is basically taking a sample and finding the best hypothesis for that sample, which is not efficient in general. Without proof, right? So finding the best Python program that fits the data, for example, that obviously is a hard problem, maybe even undecidable. So let's remember the definition of statistical or PAC learning. So we say that hypothesis class H from X to Y is learnable. And this is statistically or PAC, probably approximately correct, and both are the same thing, if and only if we have the following. So so there exists an algorithm such that for every epsilon and delta, there exists a number m that depends on epsilon and delta, such that for every distribution over x plus y, the algorithm applied to a sample S from D to the M returns hypothesis, which we denote by A of S from X to Y, such that with probability at least 1 minus delta, the error of this hypothesis is smaller than epsilon. And this hypothesis is created using the sample. The only access that the algorithm has to the data is sampling another point. And that would denote, so if it samples m times, that would denote by d to the power m. So right, so this sample is of size n. You remember the algorithm we showed that allows this kind of learning for a finite hypothesis class, right? What was it? What was the algorithm? Remind me. Alex, you remember the algorithm?
I can't remember it.
Okay. Someone else. I will pick on you one by one until someone gets. Angelos, what was the algorithm?
ERM?
Yeah, which means, so ERM means empirical risk minimizer, right? So we take a sample of size m, then we try to minimize the error on that sample, which means find the hypothesis in the class that gets it all right, because we assume realizability. We assume that all the examples are classifiable precisely. We find this hypothesis. There could be more than one. We find one, we return it. That's the algorithm. Is it efficient? Absolutely not. Right? Maybe the hypothesis class is a set of all formulas, SAT formulas of certain size, and then it's inefficient, right? To find, yeah, Elijah?
Oh, sorry. I had a question about the error definition. So what are the constraints on this error function? Is this a particular error function? Is it from a broad class of potential error functions?
Yeah, if I want to be really kind of capture everything, very general. I would say that it's learnable with respect to a certain loss function. So we'd say like with respect to loss L, and that L is from y cross y to the real numbers. For example, it could be square loss or log loss or something like that. But it's not really important. We only discussed, and the important part is if this error is defined to be that whatever the algorithm given x, that is a label, is this equal to or not equal to y? So 0, 1 loss. Okay, let's say this binary classification, 0 and 1. Y is for all we care for this class, 0, 1. That's it. Binary labels. You can, of course, generalize it to more continuous labels and general loss functions and so on. Okay. So you remember what are the weaknesses and strengths of this definition for learnability, I hope. I kind of talked at length. I was maybe in a bad mood that day. I talked about this is not a great definition because everything is, a lot of hypothesis classes are learnable, and it's kind of hard to find something that's not learnable. And if we find something, it's not really clear that this is a hypothesis class we really want to use. And most expressive classes, such as deep neural networks with finite precision or Python programs, are learnable by this definition. So it's very easy to prove too. But the caveat, the downsides are we don't get an efficient algorithm. That's what I hope to correct today. But the upshot of it is who can give me what's a good property of this definition, or what's the strength of it, if we think of it as a model for learnability? Yeah?
Maybe sample complexity. You can say something learns what you're solving.
Okay, good. So it comes with a quantitative kind of characterization. We can talk about sample complexity. That's definitely a good strength of the definition. And another strength? Joshua, what's good about it?
I guess it's nice that you want the error panels.
Sure, I mean, the error makes sense. That's a good definition, I agree. But in what sense is this a general, what is a good general property of this definition? In what sense is it very general? Yeah?
It makes very little assumptions about, for example, the algorithm, the type of error.
Absolutely, I agree. Yeah?
You also assume nothing about the distribution.
Oh, very good. Yeah. So for any distribution, this is a very strong property here, right? And that's a realistic thing, because how would we know what the distribution is like when we encounter data in the real world? It's a very hard thing to characterize. So that is a strong strength of this definition. It also requires quite a bit. It requires the error to be for every epsilon. So this can go to 0. The error that we require from the algorithm to allow us for learnability should go to 0 with very high probability. So, okay, take that in mind. Then, in a historical context, this was thought out a lot in the statistical literature, and then computer science literature, people talked about back learnability and talked about this definition and so on. And around that time, this was 80s, I would say, mid-80s. I think Valiant's paper came at 84, and he talked about back learnability. Then, I want to talk about a paradigm which is an algorithmic paradigm. The way it came about is from a theoretical investigation of this definition. But let me say more intuitively what is the question here, and then I will try to formulate it in terms of back learnability and give you algorithm for doing it. And this is the question of boosting. And the idea is, for many problems, here is kind of an observation. It's much easier to learn approximately, and by here approximately I mean rough approximation, so roughly, very rough approximation, than precisely. So let me give you an example of what I mean. Let's think of the MNIST data set that we have all these characters and we want to classify them into digits. So here is a digit, an 8 by 8 digit of the digit 1. Think of this as an 8 by 8 bitmap. And here is maybe the digit, I'm going to go with 4. Okay. So maybe it's hard to think of a machine because the 4 can be tilted in all sorts of ways, and the 1 doesn't have to be like this. Maybe this bottom line here doesn't exist, it'll still be a 1. Maybe this top thing doesn't exist, also going to be a 1. So it's kind of hard to come up with an exact characterization. But a rule of thumb, that's something that will get it slightly better than a random guess, that we can maybe do. For example, let's check this how's it called? Pixel, this pixel over here, and see if it's black or white. And if it's black, I'm going to say it's a 4, and if it's white, I'm going to say it's a 1. So of course, it's not an accurate classifier. But it will do a decent job, decent meaning better than chance. So better than chance, it's able to do. You agree? And it turns out actually that for MNIST, you can get pretty good accuracy with 4 pixels. With 4 pixels, you can classify pretty much all the 10 digits up to some pretty good accuracy. So this is some interesting study that was done. And you can imagine other scenarios. For example, let's say I want to classify an email. I want to know if it's spam. So what would be like a good rule of thumb? Yeah?
If it has some word in some list of very urgent words that appear a lot in spam, then it's spam.
Yeah, maybe if it has the word Viagra, it's spam. If it has, some Nigerian prince wants to inherit you some amount of money, then you have a few words there that will be able to classify very easily. Maybe if it's spam. Now, it's not an accurate classifier. Maybe if the word Nigeria happens there, it's a legitimate email about something happening in that particular country. But maybe there is a lot of, I'm picking on a country. I don't want to pick on any particular country. But there are these associations that will happen, inheritance, whatever. Inheritance maybe is a word that might be associated with spam. And not every email that has this word is spam, and not every email that doesn't have this word is not spam, but it's some kind of indication. And maybe you can combine them into something more accurate. Okay? So that's the idea. And how do we make it formal? So here is the way that I believe Kearns and Valiant made it formal. So here is a definition that they gave and the question that they asked. So this is the question of boosting. And for that, we need to define what a rule of thumb, what a kind of a weak hypothesis is, and it's called weak learnability. And the way I can define weak learnability is exactly the same as here. So we say that the hypothesis is weakly learnable if all of this happens, but the error, so instead for every epsilon delta, I would say for every gamma delta, there exists an M of gamma and delta, such that same thing exactly, and then I want the error of what the hypothesis that the algorithm returns to be less than or equal to half minus gamma. Gamma is some small constant bigger than 0. I'm now talking only about binary classification, 0-1 loss. And realizable setting, meaning there is a hypothesis that gets everything correct, 0 loss. You can generalize it in many, many ways, and maybe we'll get to it. Yep.
So how is this different from the original pack learnability?
So original pack learnability requires my error to go to 0. So for every epsilon, there should be some sample that will enforce I'm getting an error of less than epsilon. with very high probability. This definition of weak learnability only requires the algorithm to return something that's better than chance. By the way, half is easy, right? I can give you a hypothesis that gets it half. Throw a random coin, return the heads or tail. That will get you half correct for binary classification. So it requires very little beyond chance, and I'm not requiring this to go to 0. This doesn't have to go to 0. Maybe it sounds too easy? Question?
But it's for all such gamma, so can't we just push gamma to 1/2?
No, not for all gamma. Sorry, did I say for all gamma?
Yeah.
Oh, no good. Okay, for all delta. So there exists a gamma bigger than 0, such that for all delta. Okay, so not for all gamma, not for all gamma. Sorry, maybe that's what my mistake. So think of gamma that of some kind of 0.01 or some small constant. So this seems to be much easier, right? I mean, clearly strong learnability implies weak learnability. That is clear. But the other way around is not clear at all. And now the question is weak learnability equivalent to strong? Now this might even seem a little bit too weak, right? It might even seem a little bit too, how on earth is this? Are we able to take this definition of 0.49 accuracy and make it into something strong? So any comments or questions about this question? Does it make sense? It's an interesting question. It's not an easy question to ask, right? Well, if the answer is no, maybe it's an easy question. But if the answer is yes, it's not an easy question. Yeah?
In the binary case, the binary label case, doesn't
Right.
this mean that almost all algorithms are weak learnable? In the sense that if they're not, then you can invert them, and then they would be less than 1/2.
If they have a difference from half, yeah. If
Yeah,
they're not doing
maybe.
random guess, that's true. That's a very good observation. So actually, if you're able to always be wrong, 80% wrong, that's a very good thing, because it means you're flipping the answer will get you 80% correct, right? So in binary classification, that is correct. So any difference from half already gives you a signal. And the question of boosting is, can you take that signal and boost it to being fully accurate? Okay. Make sense? Good. So that's the question that we're asking this class. Is it clear why it's an interesting question? Well, I would say, I don't know if this was historically the motivation, and we have someone which I will introduce later in this class today, who was very important historically in the solution of this question, formulation of it. But to me, it's almost an algorithmic question. Can you do something, because it's easy to find a rule of thumb, that's an easy thing. So can you algorithmically, I would add to that, can you convert a weak learnable algorithm to a strong one and do it efficiently? And if you can do it efficiently, then you have an efficient algorithm altogether, because finding the weak rule of thumb seems like an easy task, algorithmically. As opposed to very accurate, which we don't have any good algorithm, right? You can take the best in hindsight, the ERM, the hypothesis that has 0 error, that can be extremely hard. Yeah.
Is it true that finding a rule of thumb is easy for all distributions, though?
No, absolutely not.
Yeah.
So for some problems, for example, for SAT, satisfiability, finding any non-trivial, let me see. So 3 SAT, for example, you can, let's say you want to solve the 3 SAT problem. There are many problems that, or what's better? 3 SAT is fine. So 3 SAT, you have you want to find you're given a formula and you want to know, or you want to know if it's satisfiable. So what do I want? So, okay, then the question is, so you can ask, for example, max 3 sat, or max, I think even max 2, no, let's go with 3. So you're trying to find an assignment to the variables of the formula that will satisfy a maximum number of clauses. You all heard about this problem in complexity theory or something. Here is an algorithm. Pick assignment to the variables at random, and then how many formulas is going to satisfy? Well, you can compute roughly 7/8, because you have clauses that are or 3 variables, 3 variables, 3 variables. What's the chance you got the formula wrong? You need to get all the variables wrong for the whole thing to be incorrect, and that's 1 in 8 because you assign every variable to. Am I going too fast? Stop me if I'm wrong, if I'm too fast here. I'm just kind of giving you an intuition. So finding a formula that satisfies 7/8 of the clauses is easy by random assignment. Doing constant better, 7/8 plus epsilon, is already NP hard. And the threshold between random and the gap, constant gap, is NP hard for many problems, including variants of, I believe max 2 sat is like that too, I'm not sure, but I believe the same thing will apply there. There are many problems that are NP hard as soon as you have a little bit of gap over half. In some sense, this technique that I will show you, converting weak learnability to strong learnability, has applications also in complexity theory because of this phenomena exactly. It shows that, so what we're going to show is, okay, you have a way to learn something a bit better than chance, that can be converted to a strong learner. But the contrapositive is, oh, it's actually hard to do even a little bit better than random. If the problem is hard, it's hard to do even a little bit better than random. So this kind of technique was used in complexity theory as well. But if you didn't follow what I said in the last minute, it doesn't matter. This is more intuition. More questions? Okay, so it so happens that the answer to this question is yes. So yes, and this was proved, I believe, in 1990 by Shapiri. I'm not going to give this proof over here because it's more complicated, not as efficient of an algorithm as what we can obtain and is known since then. So much better algorithms were obtained. But nevertheless, this was a theoretical breakthrough at the time and motivated people to think about, okay, so it's possible. Wow, this is incredible. We can convert weak learning to strong learning. Even though it looks much, much weaker than strong learning, maybe it can be made into a real practical algorithm. That will be the hope. So let me prove that. So I'm going to prove a reduction. I'm going to show you an efficient algorithm that converts a weak learner to a strong learner. That's what I'm going to do now. The resulting algorithm is, I would say, practical, but not the best one that we know of. And I will say something about better algorithms later on. Questions? Yeah.
Wait, you said you're going to show us an algorithm that converts weak learning to strong learning.
Correct.
How is that not a proof?
It is a proof. I'm going to prove that.
Oh, at least.
But it's not the original proof. So the original proof, 1990, was more complicated than what I'm going to show you today. I believe, in my opinion, it's more complicated. And not as good. But there was no there was no answer before that, so that's an answer. But I'm going to show you a better, I think, a better reduction. Still not the best one. So there is a better algorithm yet that I will talk about later today. Okay? So what do we know how to solve? Okay, in this course we talked about regret minimization and online convex optimization and many algorithms to solve online convex optimization or to minimize regret over prediction from expert advice or more general settings. So that's what I'm going to use. So I'm going to do reduction from weak learnability to strong using the no-regret knowledge that we have. So it's by reduction. And the reduction will take a weak learner and an OCO algorithm and convert it to a strong learner. So the setting I'm going to assume my label set is 0, 1. X is arbitrary. I'm going to have the 0, 1 loss. So L measures number of incorrect classifications. This is a classification problem. The distribution D that I care about is arbitrary and unknown. So for simplicity, let's take a sample S. S is going to be sampled from D to the M. There are M items, so the size of cardinality of S is M. And my goal is to classify S correctly. That's going to be my one and only goal. It's not going to be to get a generalization error of epsilon. It's similar than getting a generalization error of epsilon. Why is that? Yep.
Because that's the algorithm that we use to show that we get a generalization of error epsilon in the last section.
Very good. So in some sense, if on a sample I can get 0 error, that's like the ELM, the best in hindsight, or the algorithm that minimizes error on a sample. If I get 0 error there, we saw last week that it implies 0 generalization error. There is a caveat here. It needed to be hypothesis from the hypothesis class that we're learning. I will say more about that later. But for now, I'm just going to assume this is the goal. And it's not something I can do efficiently, or I know how to do efficiently. But if I have this weak learner, maybe I can do it efficiently. So that's going to be my goal. So I'm giving you an extra boost now. I'm not allowed just to search over all hypothesis class in the world and find it. My only access to the hypothesis class is via the weak learning algorithm. So is it clear what I'm trying to do? What are the rules of the game? The rules of the game is I have some distribution over a world. I have some hypothesis class. So for hypothesis class H from X to 1. So there is some hypothesis class. My only access to it is via the weak learning oracle. I asked the weak learning oracle, here are some examples. Can you weakly classify these examples? And it will return a hypothesis from the class that has error at most half minus gamma from some positive constant gamma with high probability. Yeah? Any questions? So is it clear what I want to do and why I want to do it? Yeah, Jerry?
Do you fix the sample at the start of the algorithm, or is the sample like redrawn?
Let's assume I drew it once and that's it, it's fixed. So like statistical runnability. The hope is that if I draw a large enough representative sample and I get 0 error in it, I find some hypothesis that's not too complicated, has 0 error there, it will generalize. That's the hope. And we made it formal, right? On Thursday, we made it formal. This kind of thing should happen. Yeah? So what am I allowed to do? What are the rules of the game? So I'm allowed to, actually, let me ask you, what is the only thing basically that I can modify or change, and how can I use the weak learner in an intelligent way? I mean, I can just ask the weak learner, here are the examples, classify them, and it's going to give me some classifier that classifies them, maybe half of them roughly, correct. That's no good. I want to get all of them correct. So what do you think? What can I do? Yes, Jerry.
So since you said it's like a OCO thing, I was thinking like a weak learner might be, you could draw an analogy to an expert and then combine the experts in some way. I'm not sure how you can improve much more beyond that.
that's a good idea. I mean, I like how you're thinking, but I'm kind of asking even a more basic question than what you said. And what you said is correct, actually. But I'm asking something more basic, like, what can I even do with the weak learner? I can apply it. That's no good. I mean, what can I change using my input to the weak learner that will give me something more interesting than just a hypothesis that's half correct? Yeah?
You could repeat the sample you're using because you know the weak learner is a bit random, so
Uh-huh.
you can just repeat the sample.
Okay, very good. I forget your name.
Jeff.
Jeff. What Jeff is saying, I can repeat the weak learner on different samples, for example. That's a good idea. And the reason that is allowed is because the weak learning definition and strong learning definition, as we said, see the box over there is over any distribution. I'm allowed to give it any distribution I want. And it's guaranteed to give me a margin, some kind of margin better than random. It's guaranteed, right? So I'm allowed to change the distribution. So maybe I can resample, that's true. What if I don't want to resample? But that's kind of going in the direction that I want. What if I don't want to resample? I just have these m samples. I don't want any more. I just want to get them all right. Yeah?
Do we have access to only one weak learner?
Oh, a weak learner is a think of it like, it's not only one, it's like an oracle. You call it, it returns the hypothesis. Yeah, but you can call it twice, it can return the same hypothesis. If you give it the same thing exactly, it satisfies the definition. It can give you the same thing exactly. So that doesn't help you, right? You need to call it in some kind of different way.
Maybe you have a different weak learners and ask it the same sample. Then the probability of like all of them getting it wrong, different kind of majority would come.
Yeah, that's a good intuition. So you would hope they're all independent somehow, right? But here is something important to understand. It's not guaranteed to me that they will be independent. It's not guaranteed from the definition. Definition only guarantees me this, error less than half minus gamma, right? So I give it the same sample, it will give me the same result. It doesn't have to do anything else. You have something, Kara?
Calling in different parts of the data. Like
Okay.
give it half one time and then
That's very good. That's very good. But if I give it, like, let's say, these joint parts, so it will get half minus gamma here and half minus gamma there. And overall, it's still half minus gamma. But this is the right direction. Yeah?
Just to clarify, after you run some samples through the weak learner, do you get a loss for how off it is, or just the output of the weak learner?
No. No, there is no. I mean, I can go over one by one and see how many got right and wrong. That I can do, and that is my loss. But there's no other signal that I'm getting. Okay. Yeah, Joshua.
Maybe you can do something similar to the half-half bits that you call it only on the ones that it got wrong.
Oh, very good. Very good. So that I can do. I can change the distribution, right? What if I see, okay, here are things that it got right, here are things that got wrong, then I can call it on those that got wrong again, and so on, right? Maybe something like that will be, by repeating it, I can force my hypothesis to be better and better. Now, if I call it only with those that I got wrong, that's a good idea. Half of them will be right again. But what could happen is that those that I didn't call him on, they're all messed up, right? So I could kind of have problems in the area that I didn't call him on. But that goes in the right direction. Jerry, you are?
So does that mean you should do like a hedge kind of weighting? Like
Oh, very good. So that's where I'm going to use the power of online convex optimization, okay? So you want to find the distribution. What is the key idea here is, maybe I want to find the distribution and weight it according to how good or bad the different examples are. Okay, or how hard they are, how difficult they are. Sorry, Elijah, I kept on not calling you.
Go ahead.
But you talked the whole lesson, so I want to give it to other people. Okay, any comments? So that's what we're going to do. That's kind of the intuition. And the idea is that these online learning algorithms are very clever in finding distributions that are competitive with the best. That we know already. One more remark that I want to make, and that can be removed maybe in your homework exercises. So I'll assume that the probability of success of the weak learner is 1. So it's not 1 minus delta, I'm just going to make it 1. And the reason is, it's not 1, it's 1 minus delta, but that's really not a big deal. I can always boost it to be very, very close to 1. How can I boost probability of success? Who can tell me how can do that? So there are two, remember, probably approximately correct, there are two quantifiers here. One of them is the error, accuracy, approximately. One of them is the probability of success, the probably. Alex, you have some?
I was going to say, if you make the sample larger, would that increase the probability of success?
No, not necessarily. I mean, why would necessarily give you a better probability of success? Yeah?
Just repeat several times.
Oh, good. Yeah, Bogdan, this is good. So what I can do is I can call it, and it's supposed to, here, this is really independent, okay? So I call it, probability 1 minus delta, it will give me error less than epsilon. It didn't work, I can check. Was it less than epsilon? No, call it again. And when I have an algorithm, this you must have studied randomized algorithms somewhere.
Yeah.
Somewhere in your studies you must have studied it. You have a randomized algorithm, you can boost its probability of success by repetition. You can repeat it more and more and more and take the best result. And that has great properties. If you repeat it k times, take the best, probability of success increases exponentially. So from my perspective, probability of success is so good, it's like 1 minus 2 to the 100, to the negative 100, that it's 1. And if not, you can repeat it again and again. So I'm going to assume that it succeeds. It makes my, instead of carrying over probabilities, it makes my analysis easier. And in the text, you have a complete proof with all probabilities. But this is not the significant part. So I'm going to define the following. So define weak learner of P for P being distribution in the simplex over sample S. This is equal to a hypothesis from X to Y such that the error of the hypothesis with xy drawn according to P, so this is the expectation xy from P, hypothesis of x not equal to y, is less than or equal to half minus gamma. Okay, so that's the definition of the weak learner. It guarantees that if I apply it to any distribution, in particular to a distribution P over my sample, my error is less than half minus gamma. What else do I need? Let's see. So I want to define actually that's it. So with this, let's look at the algorithm that reduces weak learnability to strong learnability, or converts weak learnability to strong. So here is the algorithm. The input, this sample of size m from d over x plus y. We have h. We don't need h, but that's actually not needed. We have an algorithm A for online complex optimization with regret. Let's call it regret of A, T. And that behaves sublinearly with T, for example, on gradient descent or hedge, or any of the algorithms that we studied. Then we do the following. For T equals 1, 2, so on up to big T. And I pick T such that 1 over T regret of algorithm is less than gamma over 2. That I can do because the regret is assumed to behave as a sublinear function of T. For example, a square root of T or log T or something like that, so that the average goes to 0, right? We have many such algorithms. Pick one, And now we do the following. So, let's also write. So P1 is going to be 1 over m times 1. I initialize it to be the uniform distribution over all examples. So now we do the following. First, we define h sub t to call the weak learner on this pt. So I call it with the distribution pt, and that gives me a hypothesis. Then I define loss function ft of p. This is over the simplex. I'm going to apply my algorithm over the simplex of dimension n. And that I define to be a linear function. It's going to be rt transpose p with rti being 0 or 1. 1 if hg of x equals 1 equals y, and 0 otherwise. So this is a linear loss function. It's defined over the simplex, and the loss, so I need to define coordinates, m coordinates. Every coordinate is defined according to this hypothesis that the weak learner gave me with the 0 or 1, right? So 0, 1 loss. 1 if it got it correct, 0 otherwise. The idea is that I want to put more weight. Why do I give it a loss of 1 if it's correct? Because of this intuition that Joshua mentioned. If something was correct, I want to reduce the weight on it. Okay. And then I applied my online learning algorithm to obtain the next distribution. So pt plus 1 is my algorithm applied to all the loss functions so far, including the one that I just defined. And then I need to say, what do I return? So I return, after big T steps, I return h bar, which is going to be the sine function of summation t ht. So this means my final hypothesis is going to be the sine. I take all ages that I've encountered along the way, see what they predict on every x, and take the sine of that, or the majority vote, maybe a majority is better. So each hypothesis says 0 or 1, and I pick whoever many say the 1 or the 0, that's what this h bar predicts. Questions? Yeah?
So why is it called loss function when it's actually the expectation of kind of like how you get it correct?
This? Or are we talking about this, or what? Which function?
Define loss function at pp.
Oh, well, if it's correct, I actually lose. That's why it's because this is a bad event from my perspective of the distribution. I want the distribution to concentrate it on the examples that are hard.
Oh, I see.
So if it's correct, it's not hard, it's easy. So I'm giving it less weight. Okay? I lose more. Winning for the algorithm, winning means finding the distribution over the examples that are the hardest.
I'm sorry.
Yeah.
What does it mean to call the weak learner on the distribution PT?
Oh, I defined it over here. So you see, weak learner of P, when I give it a distribution, it returns a hypothesis that is whose error is half minus gamma with respect to that distribution. And I'm allowed to give it any distribution I want, right? Because that's a definition of weak learnability. Do I need to, I don't need to leave it. Okay, I'll leave it there. Okay, so the theorem says that the error over S of H bar is zero. A zero error on the sample set. H bar is a hypothesis. It's an efficient hypothesis, right? And it has zero error. That's it. It's not a trivial theorem, right? It's not immediately clear why this will happen. Yeah.
So just to be clear, first following up on the last question, WLFP is saying I have an algorithm for learning a hypothesis, and at each iteration of this algorithm, I'm going to run my weak learning algorithm in order to generate a mapping.
Repeat again.
A hypothesis.
Yeah.
So in each iteration of this algorithm, we're running our weak learning algorithm in order to generate a hypothesis.
Yeah.
And then the loss function is saying, if we're running hedge, for example, I want to put more weight on the samples which it got wrong.
Correct.
Okay.
Yeah. Is that a question? No, you just want to clarify.
I wanted to clarify.
Okay.
I think there's something about the definition of FTP is tripping me up. That might just be a me problem.
Well, maybe it's the following. I'm not sure if it is adversarially defined with respect to the hypothesis. So this is an adversarial setting. But remember that in online convex optimization, we can handle adversarial loss functions, not a problem, right? We have regret even if the loss functions are chosen adversarially with full knowledge of what we did. That's fine. Okay? Yeah, any other? Okay, let's analyze. Let's prove this theorem. First of all, question to you guys. So is it clear that this algorithm is efficient? No? Why not?
Because I don't know how efficient the weak learning algorithm
Yeah,
is.
assuming that, again, so all of this efficiency thing hinges upon me being able to find a rule of thumb or a weak learner very efficiently. So suppose there is an oracle, okay, there's someone giving me this weak learner. They give it to me. I don't know, maybe it's hard, but they give it, it's done. Now I can call it, it's very efficient. So assuming that, everything here is super efficient, right? I can run online gradient descent, I can run hedge, and I don't need too many iterations before the regret becomes small, as we've seen. So that's great, right? All of that is very efficient. This is an efficient learning algorithm. That's the main difference between what we did on Thursday and what we're doing today. Okay, so now, let's look at so what do I know from the weak learning guarantee? I know that the following is true. So if I look at FT, if I look at RT transpose PT, this is at least half plus gamma. Why?
It's just the opposite of that expectation.
Exactly, right? It's the one minus that expectation, right? Okay, very good. So let's look at the average reward. Oh, let me define. So the other thing I want, so this is 1. 2, let P star be the distribution which is uniform over all misclassified examples of H bar, the final hypothesis I return. Suppose there are examples it doesn't classify. Let H bar be the uniform distribution over them. Okay? Now I can ask, what is the value of this P star? So what is summation over T, if I want 1 over T, and RT transpose P star. What can I say about this? So I claim it's at most 1/2. Why? Yeah, go ahead.
But I was just going to say at every time step there, if you had fed it P star instead of P sub T, it got all of the hypothesis ones wrong, which means the majority of those ones had to have been wrong.
Exactly right. Okay? So this is what? This P star is only over examples that H bar got wrong. H bar is the majority, right? Let's suppose it's only over 1 example. So what I have here, this RT by definition is all those examples that the hypothesis got right. Yeah? And if more than half of them are right, it's not going to be in P star. Okay? So at most half of them are right, by definition of the H bar.